studied using this approach. And it's also been used to construct solutions of the Einstein equation alternatively. So for example, at large D, black ring solutions have been constructed using this method. Okay, so the final thing I want to tell you about today is concerns the stability of all of these objects. So this is obviously posing a question, and one that's been present from the initial discovery of many of these solutions is, are they classically stable? And there's been some quite exciting progress in this area very recently. So I want to start with the black string. So remember, the black string is this object with an infinitely extended event horizon. And it's been known for quite a long time that the black string solution is linearly unstable. So what we can consider as linear perturbations of the black string, there exist perturbations which grow exponentially with time. The interesting question then is what happens non-linearly? What happens when non-linear effects take over? How does this instability evolve? And so, of course, to answer that, you have to solve the Einstein equation in full generality, which is hard, and was only achieved a few years ago by Louis Lehner and Franz Pretorius, who studied this numerically for the special case of 5 dimensions. So I'm going to warm you up for the next speaker by showing you his results. So here is the apparent horizon of one of these infinitely extended black strings, which is very slightly perturbed by a perturbation which breaks the translational symmetry. In the top left-hand corner is the time as measured by an asymptotic observer, someone far from the string. What we're going to see is that the instability is going to become strong. And let me back up with something I forgot to say, which is that people had conjectured that the possible nonlinear evolution of this instability would involve the string trying to break up into black holes. So instead of having an infinitely extended string, the horizon would want to pinch off and form an array of black holes. The problem with this suggestion is that although it's consistent with the second law of black hole mechanics, it would have to violate cosmic censorship. So pinching off of horizons is impossible classically without violation of cosmic censorship. It's for the same reason that black holes can't bifurcate in 4 dimensions. So the question is, does that actually happen? So here we go. So there we can see the horizon becoming very inhomogeneous, and it looks like it wants to pinch off, but we've still got this very thin neck connecting these 2 large black holes. Now that thin neck undergoes its own instability and forms an even thinner neck, which now undergoes an even smaller scale instability, which then is connected by an even thinner neck, and we get this hierarchy of instabilities occurring on smaller and smaller scales with thinner and thinner strings. And all of this is occurring within a finite time as measured by the asymptotic observer. Let me show you that again. So keep an eye on the time here because it's the rate of time is slowing down, so you can see this structure developing. So there we have this very thin string with a smaller black hole, even smaller black holes. You can see the clock slowing now. The structure is developing on smaller and smaller scales. And so what this seems to be showing is that we're getting an infinite amount of structure occurring on smaller and smaller scales within a finite time. And so it looks like this string really is trying to pinch off in a finite time. And so it's strong evidence of a violation of cosmic censorship in higher dimensions. I should say one slight caveat is that, of course, the string we're starting from here is infinitely extended. It's not asymptotically flat. So it would be nicer to see something like this in a truly asymptotically flat context. And that's what we'll be coming to at the end of the talk. Okay, that's the black string. What about asymptotically flat black holes? So let's talk first about Myers-Perry black holes, so the high-dimensional version of Kerr. So I told you earlier that Myers-Perry black holes are very similar to Kerr, but there's one important difference, which is that in 5 or more dimensions, there is no upper bound on the angular momentum of a Myers-Perry black hole. So these very rapidly rotating black holes are called ultra-spinning. If you look at the geometry of the horizon of these black holes, it turns out that it's become flattened into the plane of rotation. So an ultra-spinning Myers-Berry black hole looks like a pancake, a rotating pancake, rotating, so this would be in the equatorial plane. If you look near the axis of the pancake, the solution looks very much like a product of the Schwarzschild solution with a flat direction, a black brain, if you like. And so such solutions are known to be unstable against the same kind of instability as the black string, and so this strongly suggests that these rapidly rotating Myers-Berry black holes are probably unstable. So it took a while for this to be confirmed, but now linear perturbations of Myers-Berry solutions have been considered. It turns out to be much easier to study linear perturbations which preserve the rotational symmetry of the solution. But this instability was expected to be present in that sector, and indeed it is. So it's been confirmed that indeed if you have a Myers-Berry black hole in 6 or more dimensions that's rotating faster, it will have a linear instability. More recently, a harder calculation has been done, which is to break the rotational symmetry and consider linear perturbations breaking that symmetry. And one finds that this makes things even more unstable. So in the non-rotationally symmetric sector, there's a bar mode type instability, which appears at an even lower value of the angular momentum. So this is the dominant instability of these rapidly rotating black holes. So this is an important difference, and of course, from the Kerr solution. The Kerr solution is believed to be stable. Here we see that some Myers-Berry solutions are unstable. In 5 dimensions, as far as we can tell, the Myers-Berry solution is stable. So this was linear. Again, though, just as for the black string, it would be nice now to ask how does this linear instability develop when we go nonlinear? And this has been studied. So first by Shibata and Yoshino a few years ago, and more recently, Pau Figueras and his students have revisited these calculations, and they've kindly let me show you some of their results. These are a bit preliminary, they're not expected to appear until next year, but let me show you what they found. So here is the apparent horizon of a Myers-Berry black hole in the equatorial plane. This black hole is rotating clockwise, so let's now perturb it and see what happens. So that initial growth is just a gauge effect from the way this is plotted. It's not doing much, but now you can see there's a breaking of the rotational symmetry, becoming stronger. There's a bulge developing, as we expected from the linear perturbation analysis. And you can see a definite bar appearing here. So this is as far as their simulation goes at the moment, but they don't see any problem with following this much further. And what the earlier simulations have found is that if you do follow this further, is that because you've got this extended bar structure which has broken the rotational symmetry, you're going to have emission of gravitational waves. These are going to carry away angular momentum, and the solution eventually settles down to a Myers-Berry black hole with a lower value of the spin, lower angular momentum. So I'll show you that again. So again, that's just gauge, and then we see instability slowly developing into this big bar, and at this stage gravitational waves are going to be strongly emitted, and then eventually it will settle down. Okay, so that's Myers-Berry. What about the black rings? So this is again a subject where there's been a lot of recent progress. So I'm going to talk just about the 5-dimensional black ring, in other words the solution that we have explicitly. So it's been known for some time that certain black rings are likely to be linearly unstable. So it turns out you can divide black rings into 2 families, which we call thin and fat. They can be distinguished by the sign of their heat capacitive at fixed angular momentum. So thin rings look more like a hula hoop, and fat rings look more like a bagel. So some time ago, it was shown that the fat black rings would have a rotationally symmetric instability at the linear level. And for a long time, it's been expected that very thin black rings also should be unstable. And the argument here is quite simple. If you have a very thin black ring, then locally near the ring, it looks just like a boosted black string. And we saw earlier that black strings are classically unstable against this pinching type instability. So that suggests that very thin black rings also should be unstable. But it leaves open the possibility that rings that are thin but not too thin might be stable. So there's a question of whether there's a window of stability. And this window has been closed just this year by my colleagues in Cambridge, George Santos and Benson Way, who performed a linear perturbation analysis, breaking the rotational symmetry. And their results show that, in fact, there is no window of stability, and all vacuum black ring solutions are classically unstable at the linear level against perturbations that break the rotational symmetry. There's also been work in using this large D approximation to study the stability of black rings, where a similar kind of instability can be seen there. Okay, so I've explained, so I based my career on the discovery of black rings, and my Cambridge colleagues have now undermined that by showing that they're unstable. Let me now show you how other colleagues in Cambridge have been nailing, or hammering further nails into my coffin by making all of this non-linear. So again, this is work of Pau Figueras and his students, and this work is going to appear very soon, I understand. And I'm very grateful to Pau for sharing these results with me and letting me present them to you here today. And I'm even more grateful that he's sitting in the audience ready to answer any tough questions you might have. So, as I said, we can divide black rings into thin and fat. So let me start by showing you a nonlinear evolution of a fat black ring. Remember, here we expect it to suffer from a radially or rotationally symmetric instability. These rings are rotating anti-clockwise, so this way. Here we go. So that's gauged at apparent expansion, and then see wobbling a bit. But eventually the hole in the ring closes up and we settle down to a slowly rotating Myers-Perry black hole. Okay, so the ring just collapses down to a spherical black hole. This result here is what you might call the middle black ring. This is a black ring which is neither thin nor fat, so it's on the borderline between being fat and thin. And we'll see that behaves pretty similarly. So again, that's just gauge, and we have the slowly rotating stability, a bit more deformed this time, and then it just transitions to spherical topology and then brings down to a nice clear solution. So I'll show them again, show them both at the same time, so you can compare them. Okay, so just collapse down to a nice very. So I should say it's quite remarkable. These are fully nonlinear simulations solving the Einstein equation in 5 dimensions. And they are preserving one symmetry though, so it's the same, roughly the same level of difficulty as solving in 3 plus 1 dimension. Okay, so those are the fat rings. What about the thin rings? Here it gets more interesting. So here's a thin ring. Let's see what happens here. Again, remember for the thin rings, we expect to see signs of this pinching instability that the black string suffers from. So here we'll see how that works. So we evolve it, becomes very strongly deformed into this elongated shape. So you can see there's definite bar type structure appearing here. And you can also see that at this stage in the evolution, the horizon here is much thinner than it is here, so there's definite pinching occurring here. What occurs at this stage of the evolution is that the apparent horizon finding routine that Pau and collaborators are using stops working. Okay, there's nothing wrong with the numerics. The solution is perfectly fine and convergent and so on. The solution is a perfectly good solution. It's just that the apparent horizon finding routine stops working. And the reason they think it stops working is that they think what happens next is that these two lobes merge and form an apparent horizon of complicated topology with it like a donut with 2 holes in it, or a genus 2 surface if you're a string theorist. And the apparent horizon finder can't cope with such complicated topology. Nevertheless, the solution is perfectly good and they can continue to evolve it. And after a short while, that complicated topology apparent horizon, which I should say is perfectly consistent with the topology theorem, which applies to apparent horizons, it collapses to a spherical topology horizon, which is shown here. You see it's a very deformed sphere, kind of the shape of a rugby ball, an American football, and then that rapidly settles down to a Myers-Perry solution. So I'll show that again. So complicated topology at this stage, the solution continues, and then we get something settling down to rise poles. So although it looked like things were going to pinch off here, in fact they didn't, because we had this merger and then it settled down to spherical topology. But it's clear that if we make the ring even thinner, then these two bulges will be further apart, and it seems more likely that this pinching would have more time to happen. So they've made the ring even thinner. So this is, I think, their thinnest ring. And we'll see now something more interesting. Okay, so this is a slightly different initial perturbation. But you can see that now these two lobes are much further apart, and there's definite pinching occurring here. At this stage in the evolution, again, the apparent horizon finding routine breaks down. But in this case, it's breaking down because these necks are becoming very thin. Let me just show that again. Okay, so at this stage, the apparent horizon finding routine breaks down, but the numerical simulation can continue, and then by hand, they can determine the apparent horizon at a later stage using a bit more work, and this is what they find. So you can see that we've got some big bulges here connected by some very thin necks indeed. So it seems fairly clear that this is the same kind of instability as the black string instability that we're observing. So this seems to be pretty strong evidence that cosmic censorship is going to be violated in the evolution of this instability of this asymptotically flat black hole solution. Okay, so an overview of what I've told you about stability is that it's plausible that slowly rotating Myers-Berry black holes may be the only classically stable stationary vacuum black hole solutions. So that's possible. I've emphasized that these instabilities point to a violation of cosmic censorship in higher dimensions. But this isn't really the end of the story for these various complicated black holes, because this was all in vacuum gravity, and charged black holes may be more interesting, especially because charged black holes can enjoy the property of supersymmetry, which tends to make them more stable. So I mentioned earlier that there's this supersymmetric black lens solution. There are also supersymmetric black ring solutions. And it seems likely that these are going to be more stable than the vacuum solutions I'll be telling you about today. Okay, so let me just say a few more words about these topics. I just mentioned black holes with gauge fields. So many of the solutions I've spoken about can be generalized to include gauge fields. One thing I haven't said anything about is anti-de Sitter black holes. Essentially all of the solutions I've told you about can be put into anti-de Sitter space simply by assuming that they're much smaller than the anti-de Sitter scale. Of course that's not very interesting. Interesting question is what happens as you make them bigger and comparable to or bigger than the anti-de Sitter scale. And there are solutions like black ring solutions of anti-de Sitter which are being constructed perturbatively and numerically. But that's a whole other story. And then coming back to the initial motivation for all of this, which is to try and understand some of these things in string theory, and ask whether we can test the theory by asking, does it give the correct counting of microstates to account for the entropy of these solutions? So there has been work on trying to calculate the entropy of supersymmetric black ring solutions in string theory, and there are calculations which give the right answer, but they're not entirely satisfactory. For one particular reason they're not satisfactory is they don't really answer the question of what distinguishes a black ring from a topologically spherical black hole in string theory. So I think more work is required there. Okay, thank you for your attention.
Thank you very much for this very interesting talk. Are there questions? Okay, many questions. Let's start from...
Can one infer the stability of one of these higher dimensional objects by comparing its entropy to the entropy of other possible objects?
Yes, well, you can certainly do that comparison. All that really lets you do is exclude the possibility of something moving in a certain direction. So you can, obviously, an area of the horizon has to increase. So that tells you, for example, that a Myers-Berry black hole couldn't evolve to a black ring with the same spin. But it doesn't imply that it has to increase.
maybe this is a question for power for you, and you choose. But in the black rings examples that you showed last, how global is your search for apparent horizons? In other words, how likely is it that there are other trough surfaces outside what you showed us?
I think I should hand this question over to Pal, who's sitting there.
We do have our apparent horizon finding routine can handle topologically ring-like and topologically spherical-like horizons. So for the situations where you have collapsed into black hole, for some stages we can find both a ring-like apparent horizon and a spherical-like apparent horizon, and we find that the latter is outside the ring-like, but that's all we can do. Can I just make a quick remark? It's just that I have to apologize, but I think we signed the wrong movie for Harvey for the ring that sits at the cusp. I think the two movies were pretty much the same. It was probably noted by some. The one that sits at the cusp, the instability in that case is dominated by the bar mode. So you do see deformation. Yeah, the same. So the one on the right is dominated by the bar mode. So you see deformation in the shape of the ring, but not in the thickness, and the endpoint is the same, so it's collapsed into spherical black hole. So.
In 5 dimensions, there are also the doubly spinning black rings.
Yes.
So that can become extremal,
Yes.
and there are other solutions that can become extremal and asymptotically flat. Would you also expect this sort of instabilities to occur in those cases?
Yes, so the argument for the rotationally symmetric instability of the fat black rings, that applies also to the doubly spinning black rings. As far as I'm aware, the linear analysis of perturbations hasn't been done for the rotationally non-symmetric perturbations for the doubly spinning black rings. So it's conceivable there may be a window of stability there, but I would doubt it.
And these studies also haven't been done for subsymmetric black rings
No.
either, right? So we don't really know what the instability is.
Yeah, I think that would be an interesting thing to do. Slightly harder because there's a Maxwell field, but probably not much of it.
Okay, other questions? Okay, if not, let's thank Harvey.